Okay, Assalamualaikum warahmatullahi wabarakatuh. This is lecture 14 of Control System 2 class. In this lecture, you will learn about control design. Under control design, in this class, you will learn about 3 techniques only. Okay, the first one is control design by root locus method. Okay, and then the second one is control design by body plot. And then the last one is control design by pole assignment or pole placement method. Okay, the control design in root locus is conducted in time domain. Okay, the controller design using body plot is conducted in frequency domain. And the control design by pole assignment is conducted in state space. Okay, state space. Okay. So in this lecture, you will learn about controller design by root locus technique. Okay, let's take a look on this first example. Okay, for a control design, there are several methods that we need to follow. So in this example, the question asks us to design a digital controller, okay, such that the dominant closed loop pole have a damping ratio of 0.5 and settling time of 2 seconds. So we have this design requirement or design specification as, okay, we want zeta to be 0.5 and then we want setting time to be 2 seconds. Okay, setting time means that we want the system to start from 0 and then it reach the desired output within 2 seconds. And then zeta 0.5 is specified because zeta will influence the transient response, such as zeta will influence how much is the percentage overshoot, and then rise time or settling time. Okay, so it will influence the transient response. Okay, and then the sampling period is assumed to be 0.2 second. Okay, so this T sampling period, okay, the sampling time that we are using to convert from analog to digital signal is 0.2 second. Okay, this is T equals to 0.2 second. Okay, and then this part no need to do. Okay, and then obtain the static velocity error constant, KV. Okay, this is you have learned about this under chapter 6 about the steady state error. Okay, and then finally we need to find a light compositor. We need to design a light compositor so that the steady state error to the unit RAM input is less than 5%. Okay, in this system you have a digital controller. Okay, this digital controller is what we need to design. Okay, what is meant by controller design at this stage is, okay, we have the controller transfer function. Okay, if using root locus technique, okay, the control transfer function will be in this form. Okay, so what is meant by control design in this method at this level is we would like to find what is the value of this K, alpha and also beta, so that when once we found these values, okay, we can plug it into this block diagram and then we can program it in our microcontroller or our computer. Okay, and then for the plant and zero order hole, okay, zero order hole is the DAC, digital to analog converter. Okay, and then the transfer function of this zero order hole, by now you should know already, e to the power of minus st over s. Okay, and then this is the plant transfer function. Okay, and then we can denote the combination of this zero order hole and plant transfer function as g of s. Okay, so to design this controller, okay, there are several steps. Okay, the first step is to get the desired dominant pole. Okay, to get the desired dominant pole, there is a specific equation which the pole z that we need to look for. Okay, the magnitude of z is e to the power negative t, the sampling time just now, multiplied by the zeta and also omega n. Okay, the angle of the pole is t multiplied by omega d. Okay, in the question we are already provided with what is t, and then what is zeta, and what is t. Okay, but for omega n and omega d, we still don't have this information, so we have to calculate. And then we also have the equation of omega d equals to square root 1 minus omega, zeta square. Okay, this is zeta multiplied by omega n. Okay, so from the question, the settling time is already given as equal to 2 seconds, and settling time equation is equal to 4 over zeta omega n. Okay, which is equal to 4 over 0.5 multiplied by omega n. Okay, so from here we can get omega n already, which is equal to 4 divided by 0.5, divided by 2, which is 4 radian per second. Okay, so we have omega n already. Now we are left only with omega d. So omega d equals to square root 1 minus zeta square multiplied by omega n is 4. So 3.464 radian per second. Okay, so we have, this is omega d. Okay, so we have omega d already. So we have enough information to calculate what is z. Okay, substitute for z equals to e, t is 0.2 given, zeta given as 0.5, omega n just now we have just calculated equals to 4, and the angle of z is t given, omega d we have just calculated. Okay, and then by right you should get all these values. And this angle is in radian. Okay, this z is in polar coordinate. Okay, to make it easier, okay, we need to convert this to Cartesian coordinate. So to convert to Cartesian coordinate, you can just plug in your calculator to convert from polar to Cartesian, or you can just plug in the values here, calculate one by one. Okay, this multiplied by cos of the angle, okay, plus g, okay, sine of the angle. Okay, this is equivalent to 0.5158 plus g. Okay, so once we have this, okay, this is the desired dominant pole. Okay, once we have this desired dominant pole, we can sketch the root locus already. Okay, so sketch. Okay, root locus is drawn in z plane. So we have the real axis, and then we also have the imaginary axis. Okay, and then okay, we can plot the desired dominant pole that we have just obtained just now. So it is at 0.5158 and also plus 0.81g. Okay, so this point is the desired dominant pole. Okay, and then we can continue with the next step. Okay, in the next step, we need to find the pole and also the zeros of the system. Okay, so to get the second part is the system's poles and zeros. Okay, so we are interested to get this pole and zeros, we are interested in the characteristic equation. Okay, 1 plus g of z. Okay, we just need this g of z to get what are the poles and also the zero. So just now we have g of s equals to 1 minus e minus st over s, and then multiplied by 1 over s plus 2. Okay, to get g of z, so if we change this s to z, it is equivalent to z transform of this part. Okay, as I have mentioned so many times before this, if you have this term, okay, you take it out first and then change e to the power of st to z. Okay, so we have 1. Okay, so we have 1 minus e to the power of negative st is z to the power of minus 1. And then the z transform of 1 over s plus 2. Okay, sorry, s square. Okay, this one you need to get from the z transform table. Okay, but if you look at the table, okay, this table, okay, this equation is the one that we are going to use. Okay, if we look at in the table, we have just now we have 1 over s square s plus 2. Okay, but in the table it is in the format of a over s square s plus a. So we need to multiply our equation by 2 and divide by 2. So that we will have 1 over 2, 2 over s square s plus 2. Okay, this part, okay, is in the same format as this. So we can use this equation. Okay, this a, our a now is 2, our t now is 0.2. So we have to substitute a, all this a and t as a is 2 and t is 0.2. So we have to substitute for all. Okay, so just now we just rearrange this one. And then just now we have 1 over 2, z transform of 2 over s square s plus 2. Okay, this is z minus 1 over z, 1 over 2. Okay, and then z transform of 2 over s square s plus 2. Okay, we just substitute. I already show you the equation that we need to use just now. Okay, so this is equal to z Okay, this e is the exponential number, natural exponential number. So you just key in your calculator to calculate how much it is. Okay, so if you calculate this correctly, okay, this part and this part can be cancelled out. Whatever that can be cancelled out, you cancel out first. So you should be able to get 0.0703. Okay, since we need to get the pole and also the zero, okay, we can factorize this numerator. So finally, if you calculate, you should get 0.0. Okay, so from here, okay, from this part, okay, you can get what is the zero is negative 0.876. Okay, 0 is the value of z that makes this equation equal to 0. Okay, and then from here you can get the pole. Pole is the value of z that makes this equation equals to infinity. So it's 1 and also 0.6703. Okay, so we have the pool at negative 0.876, and also, sorry, we have the 0 at negative 0.876 and the pool at 1 and also 0.6703. Okay, so you can draw already. So we have a pool at 1 and then 0.6703, and then we have a 0 at negative 8, 0.876. Okay, so once we have this, okay, we need to calculate what are the angle of deficiency. Okay, so the second step is to get the system poles and zero. Okay, the third step is to get the angle of deficiency. Okay, in order for the root locus, okay, or in order for the system to reach the desired specification or design requirement or the desired output, okay, the root locus of the system, okay, must pass through, okay, the desired dominant pool, which is the point that we have found just now, the 0.5158 plus 0.4281J. Okay, the value of Z that we obtain in step number 1. Okay, so in order for this to happen, the summation of the angle of the zeros minus summation of the angle of the pole must be equal to plus minus 180 degrees. Okay, so to do this, okay, what you can do is you get the angle of the zeros and the pole. Okay, so we go back to our root locus sketch. Okay, so we can connect all these lines. Okay, this is the pole, so this is the angle of the pole. It is measured from the horizontal from 0 degree line. Okay, this is second pole. Okay, but this one is 0, so this is 0, theta 0. So we need to calculate what is theta P1, theta P2 and theta P3. Sorry, theta Z. So from here, you can get, if you look at this diagram, okay, theta P1 is equal to 180 degrees, okay, minus, okay, tangent inverse of, okay, you use your trigonometric knowledge. Okay, theta P1 is equals to 180 degrees minus tangent inverse of, okay, the height is 0.4281. Okay, the width is this one. So 1 minus 0.5158. Okay, similarly, theta P2 also 180 minus tangent inverse. Okay, the height, this one is 0.4281. Okay, over the width, now the width is this. So 0.6703 minus 0.5158. Okay, and then for theta Z is equal to tangent inverse. Okay, the height is 0.4281. Okay, divide by the width. Now the width is this. It's 0.876 plus 0.5158. Okay, so calculate this value. Okay, if you calculate this value, you should be able to get theta P1 equals to 138.52, and then theta P2 is equal to 109. Okay, this is 9.84, and then theta Z is 17.1 degree. Okay, so we need to calculate the angle of differentiation. Okay, as I mentioned just now, you calculate what is theta P1, what is theta P2, what is theta Z. Okay, sorry, this is 5158. And theta z is tangent inverse, the height and the width. Okay, which is equal to 17.1 degree. Okay, so we calculate 17.1 minus 138.52 minus 109.84 is equal to negative 231.26 degrees. Okay, so the angle of deficiency angle of deficiency is equal to negative 231.26 degree plus 180 degrees equals to negative 51.26. Okay, negative 51.26 degrees. Okay, so from here, okay, we can go to the next step. Okay, the next step is to get what is alpha. Okay, we have the transfer function. Okay, the next step is to get what is alpha. We have the transfer function of the digital controller equal to k, z minus alpha and z minus beta. So we want now to find what is this alpha. Okay, to simplify the design, okay, we can choose to cancel the pole. Okay, if we look at here, okay, there are two poles of the system 1 and also 0.703, and then we can choose any one actually to cancel, which pole to cancel. Okay, let's say we cancel 0.6703. Okay, if we choose to cancel the pole at 0.6703, so this means that alpha equals to 0.6703. Okay, for number 5, we want to find what is beta. Now we want to find what is this beta. Okay, so to cancel to get what is this beta, okay, from this angle of deficiency just now that we have obtained, okay, we go back to the root locus that we have drawn. Okay, from the pole that we choose to cancel out just now, this 0.6703, okay, we draw an angle of the angle of deficiency, so we hit 51.26 degrees. Okay. Okay, so we draw a line for this 51.026 degree, and this point is beta. Okay, so we would like to find what is this beta, and then we can find it by using trigonometry method. Okay, just now we already have theta p2, and then we can find what is the angle here. Okay, the angle here is equal to 180 degrees minus 109.84 degrees. Okay, which is equal to 70.16 degrees. Okay, so here is 70.16 degree, and the angle here, okay, you know that the summation of the angles in a triangular is 180 degrees. So the angle here we can obtain by 180 degrees minus 51.26 degrees and minus 70.16 degree. So you should be able to get 58.58 degree. Okay, so this angle is 58.58 degree. Okay, so to get beta, Okay, you can use your trigonometric knowledge also. Okay, where beta is, okay, if you look at this okay, this triangular, okay, this triangular, okay, so we can get, okay, from here we can get tangent 58.58, okay, is equal to the height is 0.4281, okay, over the width. Okay, this is the width. The width is 0.5158 minus beta. Okay, so you just rearrange this back, and then by right, if you do this, okay, this is in degree, you should get beta equals to 0.2543. Okay, this beta equals to 0.2543. Okay, so we can you can put the steps here. So tangent 58.58 degrees is 0.4281 over the width. Okay, so when you rearrange for beta, okay, you should be able to get beta equals to 0.2543. Okay, so now we have beta already. Okay, we would like to now find what is K. Okay, for K, we can use the magnitude criteria. Okay, for the as you from the beginning, we have the characteristic equation. Okay, 1 plus GC of Z multiplied by 1 plus G of Z. Okay, after we have considered the controller, this is the characteristic equation. Okay, and then this characteristic equation is equal to 0. And 1, okay, if we break this further down, 1 plus K, Z minus, okay, alpha now we already obtained, over Z minus beta now we also already obtained, okay, multiplied by the G of Z just now, the the combination of zero order whole and plant transfer function is 0.01758 multiplied by Z plus 0.876 over Z minus 1, Z minus 0.6703. Okay, so this is equal to 0. Okay, we want to find what is K. Okay, in order to get this K, okay, we can rearrange back this equation. Okay, we can bring this one to the other side, and then we rearrange this term to other side. Okay, and then if we found that there is anything that can be cancelled out, we can cancel out first. Okay, so for example, this one can be cancelled out, so you cancel out first. It will make it much easier. Okay, so rearrange this equation back so that we can get K equals to what? So K equal to, if you rearrange the previous equation, you will get K equals to negative Z minus 0.2543 multiplied by Z minus 1 over 0.01758 Z plus 0.876. Okay, and then we are using magnitude criteria, so all of this will be positive. Okay, and then we can assign this. We can assign these terms. Okay, let's say we call this term as A, and then we call this term as B, and then we call this term as C. You can just simply assign, but you need to be consistent. Okay, so at pole, okay, at the pole of 0.2543, we call it A, and then at pole at Z equals to 1, we call it B, and at 0.876, we call it C. So remember this, and then we go back to the root locus. Okay, and then just now we have at pole equal to 1. Okay, this is B. The length here is called B. And then at pole 0.2543. Okay, this from here. Okay, this one we call it A. The length of this we call A. And the length of this we just now already assigned to be C. So we need to find what is A, what is B, and what is C. Okay, so from this diagram, okay, you can see that, okay, you can see that if you want to find the length of A, we can use the equation for sine of 58.58. Okay, is equal to the this opposite, the length of this opposite edge, okay, over A. So you will get what is A. And then for B, similarly, okay, similarly for B, okay, you can get B by using sine, okay, sine of this acute angle, okay, 180 degrees. Okay, minus 138. Okay, the sine of this small angle is equivalent to the opposite length. Opposite length is 0. Equals to 0.4281 over the length of B. So from here you can get what is B. Okay, and then for C, similarly for C, okay, the sine of this angle 17.1, okay, sine 17.1 degree, okay, is equal to the height 0.4281, okay, divided by C. Okay, so from here you just rearrange back, you can get what is C. Okay, so I rewrite all these equations. Okay, to get A, okay, you can just refer back to the root locus just now, 58.58 degrees equals to the height over A. So you should be able to get A equals to 0.5071 if you calculate correctly. And then B is sine of the acute angle 180 minus 138.52 degrees, okay, which is 0.4281 over B. So rearrange back this equation back to get B. So you should be able to get B 0.6463. And then for C, you should get, okay, C is can be found by finding sine of 17.1, which is 0.4281 over C. Rearrange this C back, you should be able to get C equals to 1.56. Okay, so once you have obtained this A, B, C, okay, you can plug into the K equation. So K equals to absolute value, because we are using the magnitude criteria, okay, of A. A just now we have found. Okay, and then multiplied by B, 0.6463. Okay, this one divided by 0.01758 multiplied by C. C is 1.456. Okay, so if you do this, okay, you should be able to get K equals to 12.67. Okay, so finally, okay, the transfer function of the system GC of Z, okay, equal to K. Our K now is 12.67 multiplied by Z minus the alpha, okay, over Z minus the beta. Okay, so this transfer function, okay, this is the final answer. Okay, is the transfer function that we need to plug in into the block diagram and program in our microcontroller. So this transfer function of the digital controller here, we already found, is K67 multiplied by Z minus 0.6703 over Z minus 0.2543. Okay, so this transfer function is the one that we need to put into this block diagram or program. Okay, so we have this transfer function. Okay, so we have done the first part of the question. Okay, we have done this part. Okay, and then we need to find KV and also design a phase-lag compensator so that the steady state error is less than 5%. Okay, if you remember from chapter 6, we have the equation for KV. Okay, KV is equivalent to 1 over T, Z minus 1. Limit, since we have digital control now, we have to multiply GC of Z and G of Z as Z approaching 1. Okay, this is equivalent to our T is 0.2, Z minus 1. Sorry, this Z minus 1 should be this side. Okay, limit Z minus 1, GC of Z just now we already obtained. And then multiplied with the plan. Just now our plan is okay, and then whatever that can be cancelled out, you cancel out first. Okay. Okay, so this Z minus 1 can also be cancelled out. So once you have cancelled out all these things, okay, you can just simply substitute Z equals to 1. Okay, over 1 minus. Okay, so you just solve this. Okay, if you do this correctly, you should be able to get the value of KV. Okay, if you calculate this, you should be able to get KV equals to 2.878. Okay, so we also have done the second part of the question. Okay, so we have done this. What is KV? We already obtained. And then we are left with the last part, design a phase-lag compensator so that the steady state error, okay, this is with respect to unit RAM input to be less than 5%. Okay, so once we have KV, okay, we check first, is the steady state error less than 5% or not? If it is already less than 5%, we don't have to design a phase-lag compensator. If it is not, we need to design the compensator. So we get what is the steady state error with respect to unit RAM input, which is equal to 1 over KV. So 1 over 2.787. So you should get 0.3589. Okay, this is equivalent to 35.89%. Okay, but what we allow is only less than 5%. So that means we need to design a phase-lag compensator to push that, or to make that the steady state error to be less than 5%. Okay, this 35.89 is too high. We only allow less than 5% steady state error. Okay, so to do this, okay, phase-lag compensator, we have the transfer function for phase-lag compensator, which is Z minus alpha L over Z minus beta L. Okay, what is meant by this phase-lag compensator design is that we need to find what is this alpha L and what is this beta L. Okay, for alpha L, we can choose any values between 0 and 1. Okay, we can choose any value. Let's say we choose alpha L to be 0.9. So we need to find what is beta L. Okay, since